Hello, and welcome to this podcast from the ALLATRA Global Research Center. My name is Anastasia, and I'm your host today. And today's topic is truly fascinating for me because the atmosphere is so much more than the air we breathe. This dynamic system connects every region of our planet. The atmosphere makes flights possible, influences satellites, communication, and operation. It drives the weather and climate. The atmospheric chemistry of many of these processes shapes the air composition, influences both the environment and human health. And I'm really excited to welcome Professor Zhang from Texas A&M University. He is a leading researcher in atmospheric chemistry with expertise in atmospheric aerosols and air quality, and he made substantial contribution to the understanding of how micro and nanoplastics affect the atmospheric chemistry. His recent work on airborne micro and nanoplastics, combined with innovative laboratory studies and atmospheric measurements, is helping us to understand this field better. Welcome, Professor Zhang, and it's a pleasure to have you with us today. Thank you very much for joining us.
Thank you very much, Anastasiya. It's really nice actually to be here sharing with you through this podcast of some of the research we have been doing and also sharing with the audience. So hi, everyone.
Welcome. And to begin, it's always exciting to hear about the scientific journey that scientists made. Could you share what inspired you to study atmospheric chemistry and what questions continue to motivate your research today?
As for me, my interest in studying like environment and air started when I was in high school because I was very interested in chemistry and biology and physics. So in my college, I was trying to decide, what would be a good way for me to combine all these different knowledge together. And in general, environmental sciences is such a nice broad interdisciplinary area that you can apply all this knowledge to solve the most pioneering but also urgent issues in the world. And that's why I decided to choose this as my undergraduate major. So what I did is I had my undergraduate in Peking University, and then afterwards I continued with my PhD at Harvard University, working with Scott Martin, who was my PhD advisor at that time. So when I was at Harvard, we have to divide a little bit deeper into a subfield of the environmental sciences. And that's where I choose to study atmospheric chemistry. The reason is because for the air, so there are lots of very fast reactions happening. And then because the air is continuously moving, so this part is really fascinating for me. The other part is that every day we breathe in and out the air continuously. So what's happening in the air also has lots of impacts on our health as well. And then at that time when I was studying, so there was lots of air pollution issues all over the world, which now still do, but have changed a lot from the past 10, 20 years. So that's also part of the research. I'm very excited because it's always changing and there's always new emerging topic that is worth studying for us to understand what's in the air, what's happening, and how does that impact our health as well as climate. After my PhD, I actually received a NSF U.S. National Science Foundation a postdoc fellowship. So this fellowship was really nice. It allows me to work at different universities within the U.S. More freely and independently. So I was working at UNC Chapel Hill, University of North Carolina, and then also jointly working with aerodynamic research at Boston College and MIT, and then to jointly explore the climate impacts as well as the chemical process of different species in the air. And then that made me really realize, okay, I actually want to go into this field even deeper and have my own research lab. And so I applied for different universities, and I eventually decided to join Texas A&M as a faculty there to continue the research and building my research lab.
Yeah, that's a really interesting journey. I think for many people, atmosphere is a pretty simple system, just oxygen, nitrogen, and some CO2. But in fact, I understand how little we know, and it is continuously changing. And if we take into account the entire air column, the upper layers of atmosphere, that becomes even more challenging. So this is one of the reasons why I'm super excited to have our conversation. And could you tell us about these atmospheric aerosols? So we know that they both influence climate and health, but people know very little about them. What makes aerosols such a fascinating and challenging field of research?
So I think you make a really good and interesting point that people commonly think that the air composition is fixed and it has nitrogen and oxygen and carbon dioxide, CO2, and all these compounds. And that is true that for this majority of the species in the air, they don't change as much. And CO2 slowly increasing, but over a shorter period of time, they remain roughly the same. But what's actually really interesting is that in the air, there's this less than 1% of the compounds, including some of the organic gas, inorganic gas, and as well as aerosols. They even consider such a small portion, but they have such a huge impact on many, many things. And then, so let's speaking about aerosols, which are the main topic for today. So they actually have very, very little mass in the air. Sometimes people estimating to be less than 0.1% or even less. So it's such a tiny fraction, but they can have huge impacts. The first thing we know is that there's air quality issue, right? So these aerosols could be held into our lung, and then they can transport it through all these alveoli and vessels and be carried all around our body and affect our health. But they can also impact on the climate as well. The reason is because for the clouds to form in the air in general, you need these aerosols to serve as a little nuclear, so for water vapor to essentially condense into water droplet or ice. And without aerosols, it's going to be really difficult for these clouds to form. So if you have air that's purely free of any aerosols in the Earth's atmosphere, then the cloud will be very difficult to even make. So that's why they're very important. So people have been studying aerosols for some time. And then initially, so scientists over 100 years ago think that there must be something in the air, right, to potentially form clouds. And that's when the first part of people discover aerosols. But as time goes on, so for the past 20, 30 years, our understanding of aerosols have improved a lot, but there are still many unsolved questions that we're working on. So these aerosols, we normally think they're essentially suspended liquid or solid particles in air, and together with a little bit of air molecules around it. So that's the scientific definition of aerosol. And then in layman's words, essentially it's some small particles that's suspended in the air and then can stay there for some periods of a time. And they're different when we talk about aerosols compared with the aerosol hairspray gels, right? These are different terms, and one is more scientific, the other is what we use every day.
Yeah, and just as we talk, you dedicated a lot of time in your research and studying the behavior and properties. And I'm really curious, what led you into the micro and nanoplastics, and why do you believe that they have become such an important area today?
This is also something I'm quite passionate about. So my lab's work, we have a few different areas. And then the micro nanoplastic is actually a natural extension of some of work I've done in the past. So previously, I was working a lot on organic aerosol, especially a type of organic aerosols we call secondary organic aerosol. So these are the aerosol components in the air that made of organics, and then they coming from the reactions of different kinds of organic vapor and reacting with atmospheric oxidants, such as ozone and other species, to gradually make these organic aerosols suspended in air. So I studied a lot of their composition and also how to detect them in real time, as well as their impacts on the climate. And organic aerosols in general are important because they comprise a large portion of the total aerosol mass in the atmosphere. And then so understanding their pathway is very important for climate as well as human health. And then after that, recently, as we heard a lot of micro nanoplastic pollution in the water, in the ocean, there's studies have been done to show that for an average person, you may eat 1 card weight of micro nanoplastic every year, right? So these are the kind of questions that we try to understand. There's a lot of exposure to the micro nanoplastic into our food. But how about in the air? How much are they in the air for their concentration? As well as how do we inhale them and what are their health effects through inhaling instead of digestion? So this was one of or some of the research questions I was curious about, and that led me into this field.
It's really interesting. That was such a natural transition to the field of micro and nanoplastic. And just during this recent decade, how has our understanding of airborne micro and nanoplastic evolved? And what is our current understanding of that?
So I think initially, when people were trying to understand micro nanoplastic, it first came in the water, so in the fresh water and ocean water. And then people start to try to collect air samples. And then the first type of air samples people collected essentially is a large passive collector. The reason why I call it passive is letting the aerosols send essentially sediment onto the collector. There's no active drawing air or anything like that. So you can think of putting a big metal plate just outdoor in the air and then let it stay there for a while. So all the dust and all the micro nanoplastic particles will also condense on it. And then after staying there for a week or a month, you bring it back to the lab to analyze what are these large particles that deposit onto these passive samplers. And people found out there were some fibers and some microplastics. And then that was a first part. People said, okay, they actually exist in the air, and then they have different shapes and different composition. And then from that aspect, it motivates more people to use other type of more advanced instrument to look at how they are in the air. So people start to characterize their size. I found out that there are some sizes are larger, some are even smaller. That's why nanoplastic start to be discovered and identified in the air. And there are also some other research labs. What they do is they try to look at the composition. They found there's a polyethylene, there's polystyrene, and there are all these different types of micro and nanoplastic composition. There's just not one type. And some other labs try to look at their shape. They see this long chain fibers, but they also see this smaller round shape or irregular shape particles as well. So there has been a tremendous amount of understanding from almost no understanding at all for the past decade. And then part of my lab's work, we're very interested in real-time detection of micro and nanoplastic in the air. The main reason here is because for this micro nanoplastic, if they're very low in quantity in the air, so if you want to sample them, sometimes it will take days, weeks, or maybe even months to collect enough mass to bring to the lab. And we have some of the more advanced, very advanced instruments to study organic aerosols. And one of them is called aerosol mass spectrometer. This is an instrument that can draw in the air and start to analyze the composition of some of the aerosols in the air in real time and provide the size and also the chemical species of these different compounds. And then we essentially use this to sample the air outside our lab window. We put through a hole on the window and then connect to our instrument. And then to our surprise, or maybe it's not surprising, that we found out that there was some significant enough mass to be detected by our instrument for these micro and nanoplastic particles. And that's how we did our first real-time measurement that we published. And then after that, some of the research that I'm trying to answer is to understand what are their normal concentrations in the air and what are their potential impacts on health and the climate, and also what are their sources. That's why I recently received the U.S. National Science Foundation Career Award, which is an award for 5 years to look at all these research questions that I proposed.
First, congratulations on your award. I would really love to learn more about your studies and the progress through them, because I'm pretty sure that there will be a lot of surprising findings. So maybe just let's first talk about your work. And I saw that you have a very cool trailer with a lot of equipment. And I think any student probably would love to work there and jump into the trailer and do measurements. So what brought you to this idea? How did you come up with that?
So for this trailer, I'm actually really surprised you actually found out the information about it. So thank you for doing the research on that. And I'm actually very excited about this kind of measurement we do. So in traditional atmospheric sciences, there are three, we call it three main legs to support this atmospheric chemistry. The first part is called experiment, which we do different reactions to simulate what's happening in the air in a more well-controlled environment. So for this type of reactions, it's normally in a flow reactor or environmental chamber that we have artificial lights, UV lights, and injecting all the species and oxidants and observe them. A lot of these are repeatable. And then we want to create these repeatable conditions to make sure that we can study the reactions in a controlled environment to understand the reaction mechanism and the impact. So that's very important. Another part is to do atmospheric modeling, which people try to take in all the different parameters in the atmosphere and simulate how the chemical reaction happens in the air while the air is also moving as well. So we call this chemical transport models because it has chemical reactions inside, but there's also atmospheric movements and transport included as well with all the physics. And then, so this is also an important way to predicting, let's say, air quality, what's going to happen for the next day in New York, in Houston, or in Washington, D.C. We need to rely on these computer models to tell us the different answers. And then the third part of the leg is field measurement, which we bring our instrument into the actual air outside environment to look at what's inside. And as the sun rises and go down, what are the changes of the composition of these different species we study? And when there's pollution happening and when there's no pollution happening, what are the differences? So these three different fields or subfields connect very well with each other for us to jointly understand their atmospheric chemistry and air pollution issues. So part of my lab would do a lot of things on the experimental side. We work a lot with modelers, but my lab also does this field measurement part, which involves the research mobile lab. So field measurement, you can essentially put instrument into one site, and this site has potentially often have air conditioning. Then you put a tube from outside to draw the air in where all the research equipment are housed. The advantage of this is that you can stay at one location, just look at how different environmental parameter changes, and that's going to affect the air chemistry. But on the other hand, if you want to cover a relatively wider area, so you need some kind of mobile measurements. People have been putting this instrument into an airplane and then fly the airplane in the air at different regions, also at different heights, to look at how the air composition and all these different chemistry would change. So for instance, recently, NOAA, so National Oceanic and Atmospheric Administration, they have done a large aircraft field study, which they put their instrument into this large aircraft and fly all over Houston, Dallas, Austin, San Antonio, and western part of Texas, as well as even New Mexico to look at all the atmospheric pollution and air quality issues. But on the other hand, if you want to go into different neighborhoods, let's say we want to look at how this community between different streets and different community or neighborhoods, how their air quality are impacted compared with a different community or neighborhood within the same city, then we need somewhere in between, not this really large aircraft because it covers a really wide area, but also not a stationary site, just stay at one location. And that's where the mobile measurement came up, which my lab has been working a lot on. So we put a lot of our instrument into either our electrical van or electrical trailer that has very little emissions from engines. And then this has a line also sampling the outside air to draw all the air inside the van or the research trailer and distribute it among all instruments to analyze. So when we drive the mobile lab at each of the street and each of the neighborhood, then it can provide air quality information from each of these locations. And then overall it can provide a comprehensive map of the air quality within a city or district.
Wow, this is very interesting. And I think every resident probably who knows about your trailer would love you to drive to their neighborhood and measure air quality. So are you able to measure micro and nanoplastics with your trailer?
Yes, we have been doing that too. So we measure a lot of things. There are EPA criteria pollutants. So these are the main regulated pollutants that we measure, but we also measure all these emerging pollutants, including micro nanoplastics, PFAS, and other compounds as well.
Can you share what are your preliminary conclusions on these micro and nanoplastic? I don't know, forever chemistry, or what are your findings?
So we have performed some of the mobile measurements within Houston, and then we go to a more industrial area of Houston, and I try to look at the micro nanoplastic concentration inside these communities. So the results is still relatively preliminary since we're working on the analyzing the data and finalize our analysis. But I would say the preliminary results is that we see very high variations of micro nanoplastic concentrations across within the neighborhood. At certain locations, we saw the concentration increase a lot, while other locations, the concentration was actually relatively staying average or low. So we're trying to understand why are some areas have such high concentrations while others are less. It could be due to the nearby sources, because it could be near regular plastic manufacturing plant, and that can create some additional pollution. But it can also depend on the wind and everything. So that's one thing we found out. The second thing we found out is that when there was heavy actually burning activity, so we found all these aerosols associated with burning start to get enhanced, right? And that's very understandable. But on the other hand, we also find out that the micro nanoplastic concentration also increased as well with this burning activity. So we think that combustion process, especially burning trash or other kinds of household compounds, these are actually one of the important ways to produce micro nanoplastic in the air, because it emits lots of these compounds through this halted flame combustion process.
Yeah, absolutely. And thanks for doing those measurements and bringing this topic up, because that is extremely important. And as you describe, I really want to ask more and more questions. So I wanted to go deeper into incineration processes. They are advertised as one of the ways to mitigate micro and nanoplastics or plastic pollution. And this is definitely a big field, like a burning plastic. We know that burning even trash causes micro and nanoplastic formation. So based on your studies and based on what we know in literature, what you can say are the major sources for micro and nanoplastics in the atmosphere? And do we have spots with high concentrations of microplastic? I don't know, like seashore areas, rural areas, cities. just what are the current data showing us?
So for now, known sources of these micro nanoplastics, so includes tire and road wear, because a lot of this tire, when they actually rub on the surface of road, so they generate these little small tire particles. And the tire particles are considered as one type of micro nanoplastics. So they can actually be generated and then distributed around, the roads and highway areas. That's one way. Another way is the textile fiber shedding process. So this is more happening indoor, right? So what happens is a lot of times, one good example is when you use a washer and dryer. So when you dry all these different clothes, so you can see the lint on those filter. And the lint itself, besides containing all the fibers, it also contains different types of micro nanoplastic inside. And then if the ventilation is not well during the drying process, this micro nanoplastic could also be coming out from the dryer and distributed into the indoor environment. And then there's also degraded plastic waste and packaging materials. So a lot of times when people throw this plastic waste away, under this natural environment, they will gradually start to degrade into smaller pieces, and eventually they become micro nanoplastics and either stay in the water or in the soil or being advanced into the air. And then the agriculture films is also another way to make those micro nanoplastic in the soil and also in the air. And then one other source that people have found a lot are those sea spray aerosols. So there are lots of micro nanoplastics materials or particles in the ocean water. And then as the wind start to bring all the ocean waves, so it start to bring some of the micro nanoplastic from ocean into the air. And that's another source of micro nanoplastics. And then besides this, so recent some of the study also show that combustion process can also generate this micro nanoplastics. Let's say trash incineration or open outdoor fire. These things will make micro nanoplastic in the air as well.
And if we talk about all these sources that you listed, what would be giving a bigger impact? Is it a sea aerosol or tires? Do we have data on that?
So I would say for now, to understand which one contributes larger to the atmospheric micro nanoplastic is still an ongoing research question I should answer. My personal thinking is that it's going to highly depend on different locations and areas. So for the urban areas, I would say tire and potentially different kinds of open door burning activity, as well as degraded plastic waste. These are potentially higher contributors to the urban air. But if people actually living in those coastal areas or these high mountain area, remote areas, then it's potentially coming from different sources, including also ocean sea spray aerosols, which can transport it long term. So to understand where they're coming from is still a very exciting ongoing question that we're trying to understand. And we have some tools to look at the sources of these different compounds and try to piece up a map to understand potentially where they come from. Because after we know that, we'll have ways to reduce their concentration in the air.
So it sounds like right now we cannot tell, is it above seashore, there is a high concentration, or it is in the city, or there is a forest, or can we kind of guess or have some estimate?
I think for now, we don't have a unified, completed picture yet, but we can have some hints. For instance, in the indoor environment, I would say the textile links and textile fiber shedding, these are potential important contributors to the indoor environment due to our human activities. But for outdoor environment, I think that, for instance, we have seen that the micro nanoplastic concentration start increase when there was open door outdoor fire, when there this a fire events or smoke start to show up. So we can see that, but it's hard to generalize into the whole urban area is mostly contributed by this outdoor burning or the trash burning events. These we still need a little bit more data points to find out where they are. So I think that because there's so many different sources for micro and nano plastic in the air, that's why I think depending on whether you're near certain sources, their contribution can also start to vary across time and space.
Yeah, I understand. You mentioned the indoors. We spend indoors 90% of our time. And if we talk concentration wise, is the indoor safer or outdoor if we don't take these extreme events like nearby fires?
I would say that there's a lot of research groups have been looking at indoor air compared to outdoor air since they have very different air quality issues and different sources of pollution. And then regarding the topic of micro nanoplastics, I would share that some of research have shown that the indoor concentration can be actually potentially higher than outdoor for certain periods of time if we don't consider this outdoor different pollutions. The reason because for indoor, we have this kind of microplastic coming from synthetic textiles, where a lot of the clothes we wear has some of the fibers and plastics in them, and furnishing also has lots of plastic contribute to indoor air, and also there's lots of dust resuspension from indoor air to bring this microplastics that's already on the floor, on the surface, back into the air. So these have been some studies people have shown, but these were mostly confined with microplastics, which are larger compounds, these larger plastic particles. For smaller plastic particles, I would say that for nanoplastics, there hasn't been too much study to look at where they are yet, or when the indoor is higher than outdoor yet. So that's still an ongoing question that's worth examining.
Yeah, that's a kind of surprising for me. Not surprising, but it's really interesting um, to see that it is higher or not. But I was really hoping that to be inside is safer. I think it's most of people think this way, but we do have so many sources of microplastics in our homes. And if we look in the numbers, if we talk about the measurements on the micro and nanoplastic, could you give us a feel how significant micro and nanoplastics versus normal dust, just if we make just general comparison, and why we should care, why it is so important?
So that's also another really excellent question to ask about micronanoplastic. So for micronanoplastic, their number and their mass concentration in the air is actually quite small compared with the existing aerosols. So for micronanoplastic, their total air mass is probably just 1% or even less than 1% of the total aerosols in the air, right? But just because their mass is small does not mean they are actually not important. So there are different reasons for that. So the first part is because the usage and the production of plastic for us, for humans, are actually increasing, some people say exponentially. So with this exponential increasing, their production has been increased a lot. And let's provide an example of COVID, right? Which this contagious COVID during that time was also exponentially increasing. So over a very short period of time, you can have a large number of people infected. The same as well goes for micronanoplastic because the plastic production has been increasing exponentially. So for now, we're looking at them, but in the next 10 years or 20 years, their mass loading could increase by a lot due to this exponential increase. So we want to look at them before they become a major part of the air pollution. So that's one motivation why people actually want to know about them. The second part is even though they're relatively low in their mass now, but the plastic is very persistent. They do not decompose very easily. So when we inhale or eat different kinds of compounds or species, so our lung can actually take in different kinds of a lot of the air pollutants, but a lot of them are coming inorganics or organics that can dissolve in water and then can be transported. Eventually, they can come out of your body or being metabolized. But for plastic, they're man-made and they're synthetic. They don't dissolve in water. They're also very difficult to be metabolized by us. So they just gradually accumulate there. So even though they're low now in their mass, but over time, the exposure can be quite high because they don't go away compared with many other organic species, which they can just gradually oxidize and be removed within a matter of days to weeks. But that's not going to be the case for micro nanoplastic. So their health effect could potentially be more significant due to their persistence. And then the third part is because a lot of atmospheric processes are actually depending not just on their mass or number, but also on the properties. So some people think that these micro nanoplastics can be very effective in making certain type of clouds, which may change the climate or alter the climate. So that's another reason, despite they're low in mass, but we're curious about them.
Wow. It's a big challenge. I think when you talk about this exponential growth, as we progress and make more advanced measurements, more precise instruments, we can see smaller and smaller particles. And based on ocean research, what we observe that then we go to the smaller and smaller particles, the number of particles are growing exponentially. And we also know from the ocean studies that microplastics is getting chopped down continuously to the nanoplastics. So nanoplastics is continuously naturally rising. So extra addition to what is already exist, it just naturally forms the nanoplastics. And based on the research, we know that nanoplastic is much more toxic than microplastic. So it might be also a big concern, right?
Yeah, these are very good points as well.
When we talk about these plastics and their properties, can you tell us more what is going on when all these micro and nanoplastics gets into the atmosphere and how they're changing?
So a lot of times the process of them actually going into the atmosphere is that they can, through this degradation of this large plastic waste, a lot of times when they become smaller and smaller, so as the size starts to decrease, they can have more resistance in the air from the gravitational falling. So eventually, their size is so small that they can just stay afloat in air for significant long enough of time. That's when they actually get into air. And then other parts is that when we burn this kind of trash and things, so a lot of times there's this advection of the air going up, and with the heat process to make lots of the compounds, organic or inorganic compounds, start to gradually become a little bit more volatile under this really high temperature environment. But as the temperature starts to cool down, those volatile species start to gradually recondense to make these organic aerosols. And that's another way to make this plastic and other species in air. The sea spray part is also from the wind process. It just keeps pushing the ocean water and then makes these waves. And then these waves break down into smaller droplets that actually stay in the air. And as water starts to evaporate, what's left in the water, including some of the salts and some of the plastic and other materials, start to stay afloated in the air.
Thank you. Yeah, all your answers are giving me so much food for thinking, and thanks a lot for sharing your knowledge. That's a really amazing opportunity to learn more. So, if the particles are getting smaller, What we know from physics is that when the particle is about 100 nanometers, they are not behaving like solids anymore. And that changes their transport property. That changes the way how they act. And that, of course, affecting their filtering. Because if we have a bigger particles, then we just use a filter technology. We can have a small pore filter, remove everything. But with smaller particles, that doesn't work, right? So, what does it mean then we go to the smaller particles?
So that's a really good point to mention about how aerosol sizes change and their properties will also change. So you're right that when particles are a bit larger, they behave more like what we know as a solid ball or liquid droplet. But as these aerosols start shrinking in size, the boundaries between a particle and air molecule start to gradually smear or get blurry a little bit due to their smaller size. They can interact much more frequently with the gas molecules. So there are processes, there are a lot of studies people have done which we call aerosol physics. They try to look at these smaller aerosols, and as they become smaller, as you mentioned, less than 100 nanometers or even smaller, less than 3 nanometers or 5 nanometers, their behaviors are getting closer and closer into gas molecules. They can suspend in air for sometimes weeks to even months. And then they can actually travel in this curved way instead of like aerosol going into this linear way if you hit into a wall or resistance. So there's lots of different changes. So people have actually, and also their mass becomes increasingly small because the volume is actually quadruply decreasing as the size starts to decrease. So once they get to a certain size, their mass just becomes so little that you have to collect a certain very, very, very long time to be able to detect enough mass for the instrument to see. So these are all different challenges that we have encountered, especially when study nanoplastics. So nanoplastics are defined as their sizes are less than 1,000 nanometers or 1 micrometer. And at this size, so we actually truly go to the field that this nanoplastic can stay in the air for days, if not weeks. So which will allow them to have this long range transportation. If you emit this nanoplastic from one location, it can travel to a different continent or all over the world to other locations just within a few weeks before they can stay afloated in the air. And then but their mass is also becoming small, especially if a lot of instruments have difficulties detecting particles that's less than 50 nanometers in real time. There are some instruments can still do, but it's just becoming increasingly difficult. So these are challenges we're actually facing now to look at this really small nanoplastic particles and even a smaller size within the nanoplastic particles.
Yeah, and if we talk about small particles, how high they can travel? Just so when we talk that they are small, they can behave like a gas, and we know that there is a gas exchange up to the very upper layers of atmosphere. What do we know about these upper layers beyond troposphere and what is happening there? Is it also nanoplastics accumulated in the upper layers of atmosphere, and what can be potential effect of them?
So when we look at these small nanoplastic particles or aerosols in general, so initially people were looking at their distribution and concentration within the lowest part of the troposphere, which we call a boundary layer. So this is where most of our activities are there. So we have lots of emissions from different industrial sources, and everything within the boundary layer, we consider them to be relatively mixed because the air just constantly go up and down to mix everything. But then once you have longer enough time, so a lot of aerosols can penetrate through this a boundary layer, and then to go through this long range transport, which we call. So these are large air mass movements, let's say from the western part of the US to the eastern part through within the continent, or go across continent from North America to Europe to Asia. So then So this is on the horizontal scale of this transportation part. But vertically, there's also transportation. So the troposphere is the lowest part of the atmosphere. It covers about maybe from 8 to 12 kilometers. And then the unique part of here is that as the height increases, the temperature of the air start to drop. But once you pass through the top of troposphere, you're going to go to a layer called stratosphere, which was a little bit understudied in the past, but now has gained lots of interest. The stratosphere was very important for the ozone layer to essentially form and then to protect all of us. That's why there was lots of ozone issues in the 80s that people put a lot of efforts on the stratosphere. But recently, we have also a lot of research labs have found out that within the stratosphere, there's also lots of aerosols there, especially during these large-scale wildfire events or let's say volcanic eruptions. So it can inject a tremendous amount of aerosols into the stratosphere. Because the stratosphere, the air moves more horizontally. They don't move vertically as much. So once aerosols goes into the stratosphere, it can stay there for years before it sediment back to the Earth's surface. And that has a very important implication on climate aspect. So people have been trying to understand if the plastics are going to these high parts, what could potentially cause them to affect the climate.
Yeah, this is fascinating. And plastic can go up, but I'm really wondering about the properties of micro and nanoplastics because they are unique. They are not the same as normal pollen or dust. Could you please share more about the properties and how they affect in the atmospheric behavior? Just maybe how important the size, shape, density, composition, or electrical charge. That's a lot of factors.
Yes, so there are so many different parts of the micro nanoplastics that are interesting. Compared with traditional aerosols, they really do have a very unique shape for a lot of them. So for traditional aerosols, because we think they're mostly coming from like this liquid or semi-solid state, so they mostly retain this nearly round shape. They can still have some rough edges, especially for actually different kinds of solid particles or dusts. They can have rough edges or pollens. They can not exactly looking like spherical shape, but then they normally fit into with this like rounded shape we normally thinking or this elliptical shape. But for plastics, especially those fibers coming from textile, they really have this long shape. And sometimes they have this long string and getting twisted. So it's a very, very unique type of shape for a lot of them. So I would say that's one thing that's very different. The other thing is that for the micro nanoplastic itself, so besides those polymers that are made from the backbone of this micro nanoplastic, there's also different chemicals you put into the plastic to make them more elastic. You make them with different colors. So these plasticizers and these color ingredients are also embedded into the plastic that makes them very different from other type of aerosols. And then for the majority of the organic aerosols in the atmosphere, we normally consider them to be having some kind of fluid properties, either liquid or maybe act as semi-solid, more like pitch or ketchup or peanut butter that has this mushy kinds of phase state to it. But for micro nanoplastics, they're mostly just pure solid. And then they are not in this liquid or semi-solid phase state. They're maintaining most these very hard, rigid, solid properties. So a lot of these unique properties makes them different than traditional aerosols, but also making them challenging for their health and climate aspect because they are unique and different.
I wanted to get your perspective on the charge of the micro and nanoplastics because we know that the micro and nanoplastic have really tremendous ability to accumulate and retain charge, and just that seems to be affecting a lot of properties, how it behaves in the environment and within the living organisms. So what is your vision on the charge of the micro and nanoplastics, and what can be the effect on the atmosphere?
This is a relatively unexplored angle, but very interesting. But for now, there hasn't been too much study to look at the electricity part for the micro nanoplastic in the air. Also, plastic in general, they can retain lots of charges of them. So it's actually very possible that they can have this electrostatic charge and that makes them either repel each other or aggregate together. It can also affect how fast they can deposit into the air, and also even their interaction with cloud droplets. I think a lot of these are actually very interesting. And honestly, they're very promising open questions that I think that we need to look at them more to understand potentially how they can impact all these different processes from their unique properties compared with other organic materials in the air.
And when I looked at the atmosphere and I was studying that, one of the surprising properties for me was that the atmosphere is a truly electrical system. And it was really amazing for me to learn what is the difference in potential between lower and upper layers. And we understand that it's a working electrical system. Clouds also work on electricity, and that's a lot of processes related to electricity. And I'm really wondering what would be the effect of these charged particles if they present, small charged particles if they present throughout the atmosphere. So can you share your understandings and thoughts on that?
I think that a lot of times if they do have these large numbers in the atmosphere, one thing is that it's going to affect a lot of the behaviors of other aerosols, because some aerosols also carry charges too. So they can start to have these interactions, either repel or attract. The other thing is I'm curious to find out how this may affect lightning or other atmospheric charging process, right? So the main reason is because for lightning to happen, one of my colleagues, Tim Logan, has done a lot of it. So you have to have these separation layers of charges within the clouds, and then where the lightning can happen. So if there are a lot of micro nanoplastic aerosols, if there's are significant number concentrations, then maybe this can potentially alter the charging process to make lightning maybe even easier or harder. But these are open questions and hypothetical. But I think it shows that how interesting the micro nanoplastic can be if there are a lot of them, if our usage and production still will increase exponentially.
Yeah, ALLATRA global research centers collect data on natural disasters, including lightnings. And it was showing recent increase in the number of lightnings, especially in some of the locations. Numbers are growing, and that is significant. That's a really interesting connection that you made. And I would be really curious to see what would be your finding in this field. When we talked with you, you mentioned several times about nanoplastic detection. And I wanted to ask you, as a person who is deeply involved in all this experimental part, what is the most challenging part in determining concentration of micro and nanoplastics? Is it sampling, identification, quantification, or distinguishing them from other particles? What are the biggest challenges?
I would say one of the challenges I consider to be quite significant is their low concentration in the air. So because they have relatively low concentration, so detecting them normally requires more sampling time. And then also a lot of times when we do real-time measurements, so if the concentration is too low, it's going to be very close to the detection limit, which is make it harder to be separated out from the noise. So that's one thing I would consider. The other part is we currently don't have a 100% mature tool yet to look at them and separate them out from other organic aerosols. Organic aerosols in general, they are very complicated. They normally contain thousands of them. So people have developed different ways to characterize them into different categories. And micro-nanoplastic itself also has many different kinds of materials that can be comprised of. So to identify each type of them and then aggregate them together as one group of micro and nanoplastic as a whole itself is also challenging. And we need more tools and understanding to first be able to separate them out and then to understand in total what they are. So these are different ways that I think can be challenging for now. But then we're also working on resolving this using more advanced instruments, lower detection limit, and there are continuous methods people have developed to look at each type of micro and nanoplastic in the air as well.
Yeah, thanks a lot for working in that area because I think we really need to make progress in order to get complete understanding in the field. So I have another question. You mentioned the impact on health, and you cited that it's a lot of influence of micro and nanoplastics on atmospheric chemistry and human exposure. You mentioned that since microplastics behave differently, it will be taken by body differently. So what do you think in terms of exposure through the breathing versus eating? How do we consume more particles, through inhalation or through digestion?
So I would say that for the total mass part of the micro nanoplastic, so the digestion probably comes for more mass. The reason is because in the food or the water we drink, there are more these largest size microplastics. And then as we start to put them into our digestion system, there's more would actually travel through. But on the other hand, I was going to say that a lot of times the toxicity or the health impact between digestion and inhalation are actually a bit different. So potentially micro nanoplastic could cause more health issues through inhalation than digestion, even though we're still trying to understand this part. The reason is because when you eat certain things, eventually a lot of them will come up, right? So if you eat micro nanoplastic mixed with the food, there's the likely case that a lot of the micro nanoplastic you digested will still be removed out of your body eventually. But when you inhale micro nanoplastic, so this micro nanoplastic, even though they are relatively low concentration in the air, but then they can stay inside your lung and stay there for a long time. So the health impact on your lung can be important. The other part is when the plastic become small into the nanoplastic regime or some of the smaller microplastic, so they can deposit very deep into the alveoli of the lung, and they can penetrate through that and circulate all around the body. So in toxicology and public health, people have shown that for particle sizes similar to the nanoplastic, they can be actually circulate all over different parts of your organs and within your body. And then that's going to stay there for a long time. And for really small ones, they can actually penetrate a layer, we call it brain-blood barrier, which is a kind of a barrier between human brain and the rest of the body to prevent some of the unfriendly species going in. But once the aerosol sizes shrink down to a certain level, it can easily penetrate that area and enter into the human brain. So sometimes people suspect that this plastic accumulation can lead to this long-term health effects such as dementia as well. And these are ongoing research work people have been trying to do. So that's why I'm thinking that even though the total mass is probably higher through digestion process, but the health impact from inhalation can be significant.
Yeah, that is important concern. And we know that the concentration of micro and nanoplastics in the brain is higher than in other organs. And our brains are kind of protected from other system of bodies like head, is separated, right? But inhaling air with micro and nanoplastics, and then it can go through the nose and olfactory nerve. And that is really concerning, especially for these tiny particles. So I wanted to talk to you about the recycling because we hear a lot that this is one of the ways to mitigate, especially the plastics, micro and nanoplastics as well. And we need to have like recycling. Scientists who studied these micro and nanoplastics, they were surprised to find in the areas close to recycling facilities that the soil was containing higher micro and nanoplastics. And you mentioned that you also measured the air quality around those recycling facilities. So could you share what were your findings and how the incineration facilities, recycling facilities, and other waste management processes are affecting micro and nanoplastics? And maybe they generate new particles with a different chemical composition. Do we have enough research on that?
We know that incineration and its recycling absolutely generate new particles with different physical and chemical processes. And then for micro nanoplastics, what we have found in one of our research studies that's actually published on ESNT, Environmental Science and Technology, is to show that when the air mass coming from this incineration plant, we do see an increase of the micro nanoplastic in the air as well. So we think that this correlation potentially reveals a causation that the incineration part would actually bring out this micro nanoplastic. And that also agrees with some of the recent observation for mobile measurements when we were doing in Houston to look at when there's more fire burning aerosols in the air, that the micro nanoplastic concentration also increases as well. And then outside that, so there has been also a few other research labs that provide this kind of research, such as in University of Toronto. So people have done that. They burn different kinds of plastic materials now and try and look at what they emit. And they did find that this plastic material, once they are burned, they confirmed these micro nanoplastics can also be emitted as well. And their properties actually are very different from the original material because of the heat process already chemically altered some of the composition for this micro and nanoplastics. So I think that's one area to be potentially considering, especially for nanoplastics that are much smaller and can stay in the air for longer. The emission process could be important. And the recycling and waste management is also important because a lot of times they have two effects. One is that if it's during the open air process, so a lot of this plastic waste may be grinded or just atmospheric age into smaller pieces and being brought into air. The other thing is through the underground water and leaking process, this plastic can also mix with soil and water and eventually going to the ocean or the lake and then being advanced back into air. So these are different ways that we need to understand. I would also say that the tire wear now become a very important issue for micro and nanoplastics in the air or in general other sources of air pollution as well, especially when those tailpipe emission coming from the engines have been reduced significantly. The tire wear part start become more important.
Yeah, well, and it's interesting when we talk about this alternative for recycling facilities. If they are generating micro and nanoplastics, should we look for alternative? Are there ways to make this technology safer?
So yes, there are different ways to handle this process. There are alternatives people can do to make those technologies safer. That's absolutely for sure. The other way is, during this combustion process or trash incineration, there can be different filters being put on and air purifying process to be put on. That even we're combustion the process, but we're trying to reduce their emission into the air.
I'm an industry person and we're always thinking about the whole cycle. Basically, if you put filter, then at some point it will be end of life of the filter and you still need to find a way to process a filter with microplastic. There are also another challenges that we discussed with you when we go down to the tiny particles, then filtrations needs to become more and more sophisticated. So I think it creates really a lot of challenges. So, I think the biggest question that we hear a lot, can we reduce exposure, especially when we talk about airborne micro and nanoplastics?
So to reduce exposure, is it really good ways, like the same ways to reduce exposure to aerosols in general? So I would recommend that for indoor environment, a lot of times putting on air purifier would help a lot to reduce these different atmospheric pollutants in air. So that's certainly one of the more effective ways. And there are different type of air purifier. It actually doesn't have to be very expensive, but as long as their air purifiers can remove smaller aerosols, that would be good. So we call them HEPA filter, HEPA. These type of filters are very effective in removing smaller aerosols, including micro nanoplastics in the air. So that's being, highly recommended. And sometimes people can just make it using a fan and purchase a HEPA filter online. There are different DIY ways to make it for probably $20, $30. So it's going to be quite inexpensive, but helps a lot if people don't want to buy these commercial ones. And then the other thing I was thinking of would be helpful is to reduce the exposure to these near plastic sources. For instance, if people are going to do this washing and drying process, maybe make sure that the filters for the dryers are always checked and cleaned so it can retain as much as these fibers as possible, and also pay attention to the air quality. When the air quality is poor outside, so it's good to normally stay indoor and avoid being exposed too much to the air from outdoor as well.
And if we talk about outdoors, is it a way to reduce exposure of micro and nanoplastics?
So for the outdoor area, I would say that a lot of times when people are walking on the street, there has been studies to show that the distance of people living close to the highway can affect their health a lot. So for people living closer to the highway, which where there's lots of pollutants coming from the cars and tire, including micro nanoplastics, but also other type of pollutants. So the cardiovascular disease rate also increases. So to stay away from these sources of combustion and the highway and the car engines, these are good ways to help protect everyone from the pollutants in the outdoor air.
Professor Zhang, coming closer to the end of our conversation, I wanted to ask you what are the three most important research priorities that you see for the next decade? Or what kind of questions we need to answer before we fully understand this micro and nanoplastics impact on environment, climate, our health? So what it would be?
Yeah, these are very important questions in my mind. Are the first is from chemically. I think it's good to standardize the sampling and identification processes to look at these micro nanoplastics and look at their chemical reactions and their aging pathways in air. There are so many different technologies nowadays to look at micro nanoplastics in the air. You can visually observe them. You can use different instruments to look at their different properties and estimate their mass or number. But it would be good to cross-compare all of these different methodologies to standardize them so everyone understands what are the pros and the cons, the advantages and limitations of each technology. So I think standardizing all these are very important. And then the other part I think will be important is to understand their atmospheric processes, including how fast they chemically age in the atmosphere, and then what are these aging reaction rates and chemical kinetics, and also how does this affect the the atmospheric part affects the part in the ocean and in the soil for these micro nanoplastics. What are the contribution of the atmospheric nanoplastics and the microplastics to the total atmospheric, to total environmental micro and nanoplastics? So this is the second part. The third part is to understand the impacts on health, the impacts on climate, and then how would that actually affect the toxicology? How would that affect the lung cell and lung exposure, and would that impact on long-term health, including dementia, as well as whether the plastics may cause the cloud formation process to be either enhanced or changed. So these are the three major questions I would be very interested in learning more about, which also, some of them included in my current NSF career proposal as well.
Yeah, that's really great. And I really hope that we will progress fast in all of these directions. We do see a lot of positive feedback from EPA. There is a STORM program launched in the United States, but it's definitely need more and more resources and more scientists like you. And it's really cool to see how these things are going. Just to be positive, what gives you optimism in a field? Like what really makes you think that we are going in a right direction?
Yeah, we talk about a lot of the issues and pollutions coming from, aerosols or micro nanoplastic, right? So I think that these are things, we try to understand and they're urgent. That's why, we want to know about. But also, on the other hand, I want to share that to all the audience here that most of the time, so throughout the past few decades, the air quality worldwide, especially in many countries, are actually going towards improving because we're raising awareness of the air quality issue. And then we'll try to actively improve it. In the US, so the air quality has improved a lot over the past few decades. The emission from this car exhaust and tailpipe has been reduced dramatically due to all the development of the catalyst, also due to the Environmental Protection Agency. So they have been trying to monitoring and working with state and city and local government to make sure the air we breathe in are attainable within the criteria and also healthier. And then this also happens not just within the US or maybe Europe, but also within many other developing countries as well. In China or many parts of Asia, the air quality has also improved a lot for the past decade as well because of the awareness we have. So I think that I do believe that even though there are different kinds of issues still coming up and there are always new emerging issues due to, where inadvertently just releases into atmosphere, but I do believe that together we can find a solution to resolve this and make it healthier and better for us and also for the next generation.
Yeah, thank you so much for sharing. And it's amazing. If we are finalizing our talk today, what would be one message that you would like our listeners to take from our today's conversation?
So, I think one thing I really like about and I want to share is something I read in the past, is to say that the atmosphere is barely a very thin layer around the Earth. If you compare the atmosphere if you compare the Earth to the egg, the atmosphere is like an eggshell or even thinner than that. But yet within this layer, every living creature, including us, draw breath in it. And that's why understanding the air is such an important part for us, and then also for everyone else and every living creature on Earth.
Thank you very much for sharing. So it was a real pleasure for me to talk to you, and I learned so much. Thank you for all your insights, and especially in understanding of micro and nanoplastics. What do they do to the atmosphere and the environment? Thanks a lot for your contribution. I really wish you to progress and grow your team bigger so we can answer more questions.
Thank you so much for having me.
And to our listeners, thank you for being with us today. This field is moving quickly and staying informed matters. Links to Dr. Zhang's research and to ALLATRA report, Nanoplastic, a systematic risk analysis for human health, ecosystems, and environment are in the description. We will see you next time.